Hello everyone and welcome to this NAACL tutorial. My name is Alexei Severin and we are going to spend the next few hours and do a deep dive into the topic of text generation with text editing models. So we have 10 speakers today that come from different places. So the first big group from Google Zurich, Eric, Jonathan, Alexander, Jakub, Daniil, Sebastian, and myself. We are an applied research team working on the natural language generation and Google Assistant. We have published quite a few papers recently that introduce text edit-based models, which we'll also cover in this tutorial. Next, Yue from McGill University and Mila, she's finishing her PhD soon. Felix from Google Berlin and Shankar from Google New York office. They have published a number of papers on grammatical error correction, also leveraging very heavily text edit-based models. So overall, it's been a lot of work putting this tutorial together. So I'd like to thank all of the speakers for their hard work. And lastly, I wanted to say, to the best of my knowledge, this is the first and most comprehensive overview of what has been happening lately in the space of text edit-based models and what one can do today with text edit-based models for text generation. So with that, let's start with the goals of the tutorial. Mainly, we aim to achieve two things. So first is present an overview of the research on text editing models, where we focus on general themes rather than individual models. And secondly, we provide practical guidelines for when and how one shall apply text editing models. So here's an outline of the tutorial. I will first talk at a very high level, introducing text edit-based models and how they generally fit into the general landscape of NLP model classes. Secondly, Eric, Jonathan, Felix, Shankar will dissect a typical text edit model into its main components and talk about how one can train a text edit model. Thirdly, Daniil, Yue, Eric, and Sebastian will cover a bunch of applications such as grammatical error correction, text simplification, and so on. Fourth topic, controllable generation. We'll talk about very important things like hallucinations, dataset generation, and so on. 5, Alexander will talk about multilingual setting. And next, Jakub will talk about model latency, which I think is one of the most important reasons why someone should strongly consider and at least be aware of what the main strengths of text editing models are when one thinks about productionizing a generic text generation model. And finally, Eric will conclude with some recommendations and considerations for the future work and directions. Okay, so let's begin by answering the question, what are text editing models? So first, I want to take a bird's eye view on the landscape of NLP tasks. Very roughly, here are some of the main classes of NLP tasks that everyone is already familiar with: classification, sequence labeling, and generation. And eventually, I would like to position the class of problems that fall into the bucket of text editing also here. So classification is probably the simplest task, where the model consumes a chunk of text and produces a single label or multiple labels. Here, typically we have an encoder-only model with a single softmax layer on top. Examples are document classification, sentiment, or toxicity classification, and so on. So the next class is sequence labeling, where we also have an encoder that generates a label for each element of the input sequence. So some examples are part of speech tagging, extractive summarization, and squad style question answering. Lastly, the most broad class of tasks are generation tasks, which are modeled as sequence-to-sequence problems. Here we typically use an encoder-decoder based model, and the target output is a sequence of labels or tokens. So generation or sequence-to-sequence models are actually very flexible, and interestingly, they can basically model every other task. So, and this is exactly what pre-trained sequence-to-sequence models like famous T5 model demonstrate. So a generically pre-trained large language model, either encoder, decoder, or decoder only, can get state-of-the-art results on all kinds of NLP tasks, such as classification, sequence labeling, and generation tasks, which is actually great. This leads to strong simplification of approaches. From a practical perspective, it means whatever NLP tasks you may have, it's a good idea to start off by building on top of a T5 model or any other most recent pre-trained large language model, or at least initialize from its checkpoint. And the recent trend actually demonstrates that the recipe that works super well is basically scaling up the size of the text corpus, which is used to pre-train a language model and increase its size. It's amazing how quickly we were able to go from models like BERT, that is just a few hundred millions of parameters, to models like PALM with 540 billion parameters, and demonstrate significant gains over the previous state of the art. And one important observation is that as models get larger and larger, they become exponentially more expensive and slow to serve. So basically, they are not very practical for applications beyond demos. So to make such large models more practical, typically what one would do is to distill it into a smaller sized student model. Here, one tries to find an optimal trade-off between the model size, accuracy, and latency of the student model that meets the requirements for a given application. For text generation tasks, most often student models have a similar model architecture as the teacher model, which means that they can still be somewhat slow, as the most expensive part is the autoregressive decoder. Now the question is, for some text generation tasks, what observations can help us design better model architectures that can be significantly faster than a vanilla Seq2Seq model such as Transformer? So now let's review some examples of natural language tasks and see if using a sequence-to-sequence approach is well justified from the inference point of view. First, machine translation, where the source and the target are in different languages. Basically, here the decoder may even use a different vocab. It generates the target completely from scratch, and there is very little overlap between the source and the target. Next, let's take a look at abstractive summarization. So the core difference is that this is a monolingual task. And in fact, I would argue that outside of machine translation, there are very few NLG tasks that are not monolingual. So here, surprisingly, we see that a possible summary can be even fully extractive, where the target is reusing most, if not all, source tokens. And this is highlighted in green. So let's take a look at sentence fusion, where basically by the task definition itself, we simply stitch sentences together, where the only thing that the model needs to do is generate some glue phrase and maybe perform pronominalization. So already here, generating the target completely from scratch feels wasteful, as most of the source can be simply copied to the output sequence. Finally, let's take a look at another task such as grammatical error correction. So here, again, the model only needs to make some edits. No need to generate left to right the entire target sentence. Okay, so let's kind of recap and enumerate all the observations we can make from here. So most NLP tasks besides machine translation are monolingual. For many NLG tasks, sources and targets often overlap, where basically generating the target from scratch is wasteful. And secondly, we can actually reconstruct most of the target from the source via very basic editing ops like keep, delete, and insert. And here below, you can basically see this example of how sentence fusion can be actually mapped into a sequence labeling tasks where we generate a sequence of edit operations to basically transform the input into the output. Okay, so I think like we're ready to define already what text editing models are. So text editing models generate natural language by applying edit operations to the input text to produce the target text. It's very simple, but let's kind of review some of the key assumptions where it makes sense to apply text editing models. So basically the key assumptions that text edit models make is that there is a high overlap or some degree of overlap between the input and the output. And there's all kinds of flavors of model architectures in text editing, but basically they all try to integrate this kind of inductive bias into their model architecture to be more efficient. And so in text editing models, most of them, the way generation work is it's basically split between the encoder and the decoder. So the encoder is doing part of the generation. And the key benefit of this is just one, and I think it's the main one. There's others, and I'll talk about them as well, is basically by opting for a text editing model in favor of Seq2Seq model, you get faster inference, and most often on par quality. So here is some example applications that fall into this bucket of text editing tasks. So grammatical error correction, I already mentioned, text simplification, sentence fusion, style transfer, sentence splitting, rephrasing, fusion, text normalization, summarization, post-editing for machine translation, and many, many others. So we'll review some of them in the later parts of the tutorial. So, okay, so where does text editing fit on this landscape of NLG task classes? So it's somewhere in between the sequence labeling and generation, where basically the task is to do sequence labeling or tagging and insertion. And typical models, they can be encoder only or encoder plus decoder. But in terms of latency, text editing models, they lean to be as fast as sequence labeling model, or somewhere in between the Seq2Seq model and sequence labeling model. Next, I want to highlight why text edit models are interesting and are worth looking into. So these attributes are going to be covered in more detail in the later parts of the tutorial, but on a very high level, what I wanted to mention is that very often text editing models are more data efficient compared to Seq2Seq models, and which means they require less training data. They deliver very significant latency savings. They are typically faster, the Seq2Seq models, by a large factor. So naturally, by design, most text editing models tend to be a bit more faithful in their ability to like circumvent hallucination by basically constraining the generation process. And it also, like in some scenarios, it's easier to control text editing models because there's more knobs that you can control through the generation process. Okay, so with that, I would like to hand over to Eric, who will talk about model design.
Thanks, Alexi. Hi, I'm Eric. So next, I'm going to go through some generic design patterns across different text editing models, and we're going to give a high-level overview of what these common components of different methods are, how do these methods differ, and what similarities they have. But before I go into the overview, let me start by going through briefly one particular method. And this method is called LaserTagger. It's something we published in 2019. And yeah, so this has motivated a lot of the work we've done within our team afterwards, some of the limitations of LaserTagger. So what motivated or led us to develop LaserTagger was the problem of sentence fusion that Alexi already mentioned. So just to recap, if you have, for example, a query like Einstein birth and death, you may want to answer this with multiple different aspects related to this query. And instead of just concatenating these different aspects or sentences describing different aspects, the answer would sound much more natural if you actually repeated some of the, removed some of the redundancies and added some glue phrases to get an answer such as Albert Einstein was born in 1879 and he died in New Jersey at the age of 76. Okay, so we started to look into this problem, and the first thing obviously that we did was to train a regular transformer model. This worked pretty well, but we did notice that the model would sometimes hallucinate, sometimes not produce very coherent outputs, mainly because we didn't have that much training data. And back then, we didn't have great pre-trained transformer models like T5. Okay, so however, if you look at this problem more closely, you notice quickly that there's a high level of overlap between the answers and the fused answer. So in order to produce the fused response, what you mainly need to do is to actually just delete the repeated phrases and add some short glue phrases between the sentences. So this led us to approach the problem by, rather than generating the output from the scratch, predict edit operations applied to the input tokens or input words. So how LaserTagger works is that first you would encode the input, each input word, then you would predict a tag or an edit operation for each word, and then you would realize these edit operations to produce the output. So in this particular example, the model might predict, for example, to replace the period between the two sentences with the phrase "and he" and delete the Turing that is repeated. All right, great. So to go a bit more into details, basically, what are the key ingredients behind LaserTagger? First of all, what you need to do is that typically you'd have some source target text pairs that you use to train your model. But now that we're training a text editing model, we first need to convert the target texts into target tag sequences or edit operation sequences. And Felix is actually going to talk a bit more in detail about this step. So then what are these tags or edit operations? Well, in LaserTagger, we consider a base tag, either keep or delete the word, and then an added phrase, which is combined to the tag. So that in total, the number of possible tags you have is 2 times the size of the set of possible phrases. And this set of possible phrases or the phrase vocabulary is something we define beforehand, and it has the advantage that the model is only allowed to add these things, so it gives you some control over what sort of outputs you can expect. So the model wouldn't hallucinate arbitrary stuff, which is something that Sebastian is going to talk about in more detail later in this tutorial. In order to get this phrase vocabulary, we optimize it with the goal of keeping it as small as possible while covering as many of the training examples as possible. Then finally, as the tagging model, we use BERT, and we consider 2 variants, just the vanilla BERT with the softmax layer on top of it to predict the tags, or additionally having a 1-layer transformer decoder to make it autoregressive. And Jonathan is going to give you some results on this later. Okay, so that's LaserTagger in short. Some limitations that you may have already noticed would be things like the realized text is not always supernatural, not always so natural, because we only have a pre-trained encoder, but the insertions, the model has to learn it only from the training data. So if you don't have too much training data, those wouldn't be very natural necessarily. And there's kind of no language modeling component that would ensure that the outputs look natural. The second thing is that although on one hand, this limited phrase vocabulary has some advantages, on the other hand, it can be too restrictive in some cases. So for example, for things like grammatical error correction, the set of possible insertions might be so large that it's just not realistic to capture with a small phrase vocabulary. And by the way, usually the sizes of phrase vocabularies that we considered were something around 500 phrases. Then finally, if you want to reorder text, this is also very complicated because you would first need to delete the phrase and then insert it at a different position. And moreover, it has to be in your phrase vocabulary. So then some of the follow-up works address all of these individual limitations. All right, so now let's zoom out a bit and talk about what the generic components that different text editing models share are. And you can divide this roughly into 3 components. So first is the encoder. And compared to standard sequence models, I would say that in text editing models, encoder does much more of the heavy lifting than in normal Seq2Seq models, where actually often you have like decoder only models. So what are the tasks or the responsibilities of the encoder, or the questions related to that? I would say there are at least 3. So what are the edit operation types that the sequence labeling method or the tagger has to produce? Is it autoregressive or feed-forward? Jonathan is going to talk more about that. And then more specifically, what is the exact tagging architecture or the sequence labeling architecture that you use? Then the second component, which is optional, so actually not too many of the existing text editing methods have this, but I mentioned that one limitation of LaserTagger was that it's not able to conveniently like reorder words. So some models have a pointer mechanism which allows you to also produce different orders while reusing the source tokens. And then finally, some models have a separate decoder to do the insertion. So you have the encoder which decides like which tags to keep, words to keep and delete, but then a separate decoder which does all the insertions. And let's start with the encoder. So first, what are the most common edit operation types? And I would say there are 4 edit operations that almost all of the existing text editing models have. So first, there's the keep operation, which keeps the current token. Then second, delete, which deletes it. Then third, there's a replace operation, and this comes in 2 flavors. So either you can have replace plus the word or the phrase with which you replace it, like we saw in LaserTagger, and like, for example, a getter, which is a follow-up method for grammatical error correction uses. Or then you can have just the generic replace operation, and then you would have a separate insertion component which would decide with which to replace the token. Then finally, you have append or prepend. Usually models choose one of these. And here you would either append before or after the current token some new word or phrase. And like with the replace, you can either have this combined with the phrase to append, or have a separate insertion model. So let's talk about the first approach for replacing and appending or prepending, where we also predict already kind of on the encoder side what is the phrase or word that you're inserting there. So with LaserTagger, this set of phrases, as I mentioned, it's optimized based on the training data, and you can see the most commonly inserted phrases on the right for 4 different data sets. The first dataset is DiscoFuse, which is a sentence fusion dataset. And here you can see that the most commonly inserted phrases are things like punctuation, discourse connectives, and pronouns, which is something you'd expect. Then, for example, for grammatical error correction, the words are usually punctuation, articles, prepositions, things that people often get wrong writing English. Okay, and comparing this sort of with the other approach that we'll talk more about later, the advantage of having this limited restricted phrase vocabulary, as I said, is that it gives you more control over what the model is able to insert. Then on the other hand, the downsides of having this restricted phrase vocabulary is that if you have an application that requires a very diverse set of insertions, this vocabulary has to be very large. And especially if you need multi-word insertions, the size grows exponentially if you consider all possible combinations of words. Okay, the other limitation of this is that it can be hard to leverage any existing pre-trained large language model checkpoints. So basically, the model needs to learn how to use these different tags to decide what to insert. So some of the follow-up works address kind of both of these issues. So finally, what I wanted to mention is that some models also introduce custom edit operations for the particular task at hand in order to make the task easier to solve and make it more sample efficient to solve the task with text editing and more accurate. So for example, again, in the LaserTagger paper, one of the tasks was sentence fusion, and we found that having a separate operation for swapping the order of sentences is actually very beneficial. So we got like 10% improvements on the fusion accuracy by having this. So to give an example, if you had an input like Dylan won Nobel Prize, Dylan is an American musician, now the target would be to introduce a relative clause to get an output like Dylan, an American musician, won Nobel Prize. So here, what the model would need to do without having a swap tag would be to first insert the phrase, comma, an American musician, comma, between the words Dylan and won, and then delete the same phrase at the end of the input sequence. And first of all, the model has to have this full phrase in its phrase vocabulary to be able to do this in the first place. So you realize that if this is a common phenomenon in the data, you need to have a huge phrase vocabulary to have all possible relative clauses in it. All right, but yeah, then with swapping, you can actually swap the order of these sentences, and then you just need to do few deletions and add commas in order to get the output. All right, so then a second special operation that was also discussed in the LaserTagger paper is to have a separate operation for pronominalizing entity dimensions. And here the idea is that rather than the model having to guess what the gender of the entity is, we can have a separate knowledge base from which the model can then, during the realization step, look up the gender of the entity and then choose the appropriate pronoun. This also makes it easier to do postfixes in case the model misgenders someone or the pronoun needs to be updated, so it has multiple benefits. And finally, for grammatical error correction specifically, multiple custom edit operations have been proposed. Here's a one, and you'll hear more about these later in the application section. So one is noun number singular, where the model would convert a noun into a singular form using some kind of external lookup table or some kind of automatic inflection tool. All right, so that's all for the edit operation. And next I'll pass it to Jonathan, who's going to talk about various tagging architectures and autoregressiveness.
I'm going to talk about tagging architectures, particularly focusing on autoregressiveness. There are two major types of text editing models, autoregressive models and non-autoregressive models, where autoregressive models condition on previous predictions. So in our case, predictions are tags. So for instance, at time step 2, we know what tag we predicted at time step 1. These are based on Seq2Seq models and are generally quite slow. In contrast, non-autoregressive models don't condition on previous predictions. Instead, they predict all the text editing operations tags simultaneously. These generally use feed-forward neural networks, and while they're prone to errors, they're generally a lot faster. In particular, we're going to focus on 3 models, Edit5, Felix, and Seq2Edits. However, before we do this, I'm just going to talk about LaserTagger, as LaserTagger has both an autoregressive and a non-autoregressive version. And this lets us have a direct comparison. So across 4 tasks, the autoregressive version outperforms the non-autoregressive version. This can be up to 7% improvement, or it can be as little as 1% improvement. However, this improvement comes up at a significant latency cost, taking about 40 times longer on a GPU, going from 13 milliseconds to 535 milliseconds, really highlighting the trade-off between speed and performance. So how do non-autoregressive models work? They're set up as a sequence labeling task where we encode a source sentence, and for each hidden state, usually representing a token, we predict a label, and we normally predict this using an argmax. So how do we encode these source sentences? Normally we use a pre-trained model, normally based on transformers. So this pre-trained model could be BERT or it could be XLNet. And after encoding the source sentence, we get a sequence of hidden tags where each hidden tag represents a token. On top of these hidden representations, we apply a single layer feed-forward neural network, where the output size is usually between 2 and 1,000 tags. And just to highlight that each hidden state, each token gets a single tag. And this can make it difficult to generate arbitrary outputs because we can only apply one tag to each hidden state, and we lose compositionality this way. Another problem with non-autoregressive models is agreement. So say we have the task, a GC task, where we have a sentence, we have an apples, and we want to fix this. So a non-autoregressive model, because it doesn't know about the previous predictions, might change and to some and apples to apple, therefore producing a non-grammatical output. In contrast, an autoregressive model can say, okay, we predicted and previously, we know now we should predict apple, or we predicted some previously, we know we should predict apples. So how do autoregressive models work? Well, we encode the source sentence, and then we decode edit by edit, conditioning on the previous edits. And how do we encode this and decode this? Normally, we use transformer models or RNNs or CNNs. Edit 5 used T5, and Lewis used BART. So to really highlight what is going on at each decoding step after encoding the source sentence, we have to repeat this operation for each decoded edit tag. So what we do is we input the previously predicted token. In our case, this would be a representation of the edit. We then apply self-attention. We then apply cross-attention after this. And finally, we do an argmax. And again, because we're conditioning on previous predictions, we have to do this one after each other. We can't do this simultaneously. And this is what leads to increase in latency. An additional approach, which is semi-autoregressive, is iterative refinement, where we apply the model's outputs. We input a source sentence to the model. We get an output sentence. We then input this output sentence to the model again, and we can repeat this as many times as we like. However, noting that each time we feed it through the model, we're increasing latency. And additionally, from table 4, for a GC task, we can see that after the third iteration, we don't get any further improvements. This can be used with any types of models, but are generally used with non-autoregressive models. Next, we're going to talk about reordering. So most text editing models apply their edits left to right. But what happens if we want to reorder the source sentence? So imagine we have last year, I read the book that is authored by Jane. We want to change it to Jane wrote a book, I read it last year. So without reordering, what happens is you have to delete a large amount of text at the beginning and then insert it later. But what happens if we don't want to do this insertion, if we want to minimize the number of insertions? Well, this is what reordering lets us do. And reordering lets us apply large syntactic changes to the source sentence, such as the example to the right, as well as smaller changes, such as changing John and Mary and changing it to Mary and John. So how do we do this? Well, in autoregressive setups, we use a pointer network, which came out in 2015. And what we do is we encode the source sentence, and then we start decoding. And when we're decoding, we apply cross-attention to the source sentence. And we select the token with the highest attention, and we copy it to the decoder. And something to note is that we can copy the same source token multiple times. And how do we do it in a non-autoregressive setup? Instead of having a decoder, we just use the encoder. We use self-attention instead of cross-attention. and we daisy chain this self-attention. So for each source token we say what token should appear after it. So in this case, we have the beginning token, CLS. We say what do we want to appear after CLS, the. So the CLS token attends to the attends to heart attends to three to layers. And in this way, we can follow this chain of pointers to form the output sequence. And to highlight that this attention is applied all at once, it's non-autoregressive, so it's quite fast. One downside to this approach is that we can only copy each source token once. So I'm now going to talk about decoders and inserting arbitrary words and phrases. So in contrast to tagging, we're really inserting from an open vocabulary, not from a limited set of tags. So generally, a tagger predicts where to insert, and a separate component is used to decide what to insert. There are many different architectures that are used for this. However, in this talk, we're going to focus on Felix, Seq2Edits, and Edit5. So Felix uses two separate models, a tagging model, which is based on BERT, and it uses keep and delete tags and a reordering concept to produce a new output string, which is then fed into the insertion model, which then non-autoregressively predicts the missing tokens. And this insertion model is based on BERT and really leverages this pre-trained objective of BERT of filling in the missing masks. So how it works is basically we have our tagger, which then produces a new output string. In this case, we have deleted tokens which are bracketed. And then the main thing to focus on is these mask tokens, whereas the tagger says we want to insert two new tokens. So two mask tokens appear in the output string, and the inserter's job is to fill in the contents of these mask tokens. It does this non-autoregressively. So it predicts the contents of these mask tokens simultaneously. In contrast, we have Edit5, which has an autoregressive decoder, meaning we predict in newly inserted tokens one after each other. Basically, what happens is we have a joint model that does both the tagging and decoding. However, we still have these two steps of keeping, deleting, and then inserting, whereas keeping, deleting happen on an encoder, and then inserting is done via an autoregressive decoder, which attends to the encoder. The decoder in Edit5 case is responsible for where to insert new text. So it attends to the encoder, where the encoder represents the source sequence and the edits. It says, I want to decode after position 0. So that's one time step. Next time step, what do I want to insert? The next time step, okay, now I want to decode after position 2. What do I want to insert? One time step is, next time step vary. And at the end, we reassemble the target sequence by combining the reordering, the tags, and the newly inserted tokens. I'm now going to pass over to Felix, who will talk about Seq2Edits.
Seq2Edits is another edit-based model that is using an autoregressive decoder. The representations of the edits, however, are slightly different from Edit5. In this model, all edits are represented as span-level replacements. Insertions are replacements of an empty span, and deletions are span replacements with an empty string. Seq2Edits is similar to a regular Seq2Seq model, but it has 3 different output tapes instead of 1. One output tape predicts the span end positions using a pointer network. Another tape predicts the replacement tokens, and there's a third output tape that is used for explanatory tags. For instance, in the GEC example on the left, Seq2Edits would tag the replacement of dream with dreams with SVA, a subject-verb agreement tag, to indicate that dream has to replace with dreams in order to make it agree with the subject. Seq2Edits was tested on a range of NLP tasks, so the tag set differs depending on the task. Seq2Edits can be up to 5 times faster than a regular Seq2Seq model, because large spans that are simply copied over from the source sentence are represented with a single step. Okay, Let us zoom out a bit and see how the methods we've discussed compare to each other. Here, we are just providing a high-level overview of how the methods differ by categorizing them along multiple dimensions, like non-autoregressiveness, whether or not they use a pre-trained decoder, support word reorderings, are supervised or unsupervised, or whether or not they are English language specific. We've already discussed some of these models and the ways that they differ from each other. For example, non-autoregressive models like LaserTagger are often much faster than autoregressive ones, but they tend to have a limited expressiveness. Not all possible mappings from source to target sentence can be represented. Semi-autoregressive models like additive5 try to sidestep that limitation with a two-step approach. The first step is non-autoregressive, followed by an autoregressive model. Most more recent work is based on pre-trained models like BERT or T5. We have also already seen two models that have special support for word reorderings, additive5 and Felix. In all the other approaches, word reorderings usually have to be represented as a deletion of the word and an insertion of it at another position. In later sections, we will also discuss unsupervised models like LUS and MASCA, and models that are not language agnostic, since they use special language-specific edit operations like Seq2. In this section, we will discuss how to convert the target text to target edits. The edit-based models we have seen so far are all supervised, but the training data for the NLP tasks they are tested on, like simplification, GEC, sentence splitting, and fusion, etc., are usually only available as parallel text, pairs of full source and full target sentences. How do we prepare the training corpora to make them amenable to edit-based model training? That question really boils down to how can we convert the target sentence to target edits. The source sentence is usually provided as is to the model. The central question for this conversion is how the model represents edits, as most models from the previous section differ in that regard. They use different edit operations, like any subset of insert, delete, replace, append, prepend, reorder, etc. They use either token level or span level edits, and some can associate edits with additional explanatory tags. Therefore, the conversion to edits depends very much on the model. Here, I'm trying to abstract away from these differences and explain the common ground for the data preparation of most edit-based approaches, with the example mapping from after many years, he still dreamed to become a superhero, to after many years, comma, he still dreams of becoming a superhero. Most approaches are based on the Levenshtein matrix between the source and the target sentence, or some variation of it. The Levenshtein matrix is a byproduct of the algorithm to compute the Levenshtein distance, i.e. the minimum number of insertion, deletion, and substitutions that need to be applied to the source sentence to transform it into the target sentence. That algorithm is a dynamic programming approach that builds up a matrix from top left to bottom right that contains the edit distances of string prefixes. Each cell can be computed using its top, left, and top left neighbors by taking the minimum of 3 costs. The top cell plus 1, shown in blue in the slide, that would correspond to an insertion at that position. The left cell plus 1, shown in purple here, that would correspond to a deletion at this position. The top left cell plus 1, if the source and target tokens at that position do not agree, like in this case, he and comma do not match, shown in orange in this slide, or otherwise the top left cell plus 0 because it is a match. So in this case, that would evaluate to 0 plus 1, the orange case, meaning that the edit distance between after many years, comma, and after many years he is 1 due to a single substitution of he with comma. You can use that rule to compute the full matrix, and at the end, the full sentence edit distance is in the right bottom corner. But you can also use this matrix not only to compute the distance, but also to trace back which edit operations caused that distance. A diagonal step is a match or a substitution, a vertical step is an insertion, and a horizontal step is a deletion. It is important to note that this path through the matrix is not always unique. Different minimal edit operation sequences may represent the same mapping. A simple example is a replacement of two subsequent words with another word. This can be a substitution of the first word and the deletion of the second word, or the deletion of the first word and the substitution of the second word. These ambiguities significantly affect model quality and have to be resolved in a way that is as consistent as possible. Another, more intuitive visualization of the minimal path through the Levenshtein matrix is an alignment between source words and target words, which can be obtained by simply connecting words that correspond to diagonal steps along the optimal path in the matrix. For a simple token-level edit operation set like insert, delete, replace, and keep, the alignment can be directly and unambiguously mapped to the sequence of edit operations. Each alignment link becomes either a keep or replace operation. Unconnected source words are deletions, and unconnected target words are insertions. Span-level edits with the same set of edit operations can be derived by merging all subsequent token-level edits of the same type, as shown here. A span-level model would represent the three subsequent keep operations for after, many, and years with a single operation. Whether or not to use explanatory tags can also have an impact on the extracted edit sequences. For example, by replacing the phrase dream to become with dreams of becoming was a single operation on the previous slide, a system that uses explanatory GEC tags would break that down to 3 edits, as each corresponds to a different GEC error type: subject-verb agreement SVA, particle error part, and a verb form error. Some edit-based models, like Seq2Edits, represent span-level edits using the start and end positions of the source span. That increases the overhead for representing change text, but unchanged spans do not need to be represented at all, so no keep operation is necessary. Another way to get more compact representations is to equip the model with a way to reorder words. In this example, most edit-based models would need to delete the word long and reinsert it again at the end. Edit-T5 as an example of an edit-based model with reordering capabilities can avoid this by a single reordering operation that directly moves the word long to the end. Edit operations that use integer positions into the source sentence for identifying source spans or for reordering usually need a more complex model design. The numeric arguments are often learned by using pointer networks instead of separate position symbols. I'll now hand it over to Daniel to talk about applications.
We will now look at the main tasks that text editing methods have been applied to in the literature. There is a loose dependency between the text editing methods and their application tasks. Some methods have been presented as methods for solving a specific task, for instance Seq2 for solving grammatical error correction. Other methods have been presented as general-purpose text editing methods, for instance LaserTagger. These methods have been applied to a variety of tasks out of the box. The general methods can also typically be tailored for a specific task, for instance by introducing task-specific edit operations. For example, the Seq2Edits paper and the PI paper have proposed modifications that are specific for the task of grammatical error correction, but they have been applied to other tasks without these modifications. We will now briefly look at the definitions of the application tasks and then examine some of these tasks in more detail, including what type of modifications and tricks have proven useful. The task of sentence fusion is to join several independent sentences into a single coherent piece. Apart from copying over from the input text, the model needs to remove any redundancies, insert discourse connectives, replace names with pronouns, and possibly reorder phrases. One characteristic of this application is that the set of inserted phrases is typically small, so this would include discourse connectives and pronouns. Sentence splitting is a problem that is in a way a reverse problem to sentence fusion. Here, a longer sentence needs to be split into 2 coherent sentences. In text normalization, the model needs to verbalize the written text. This includes spelling out currencies, numerals, dates, measurement expressions, and so on. In text summarization, a longer piece of text, for instance a paragraph, needs to be rewritten into a shorter summary. This application is actually borderline suitable for text editing methods, because a good summary may typically look like something written from scratch, rather than something obtained by modifying the input text. However, the earlier methods for text summarization used so-called extractive summarization, where basically the pieces from the input text were selected to be included in the summary. In this way, those early methods can be seen as precursors of the modern text repair. The task of machine translation automatic post-editing is to correct the systematic mistakes that occur in the output of a machine translation system, with the goal of improving the quality of translation. We will now examine a few applications in more detail, starting with grammatical error correction. The task of grammatical error correction is pretty self-explanatory. On the source side, we have a sentence that has some grammatical mistakes in it, and on the target side, we have a corrected version of the same sentence without grammatical mistakes. In the public datasets for this task, the source sentences are typically produced by the language learners and thus contain mistakes that language learners typically make. This task is actually well suited for text editing because of the high degree of overlap between inputs and outputs. The model often needs to just change a word or two or swap the word order while the rest of the sentence is copied over. As a result, a number of text editing papers have reported results on this task in the last couple of years. The results have typically been competitive or state-of-the-art, and the main highlight was an order of magnitude inference speedup. As we suggested earlier, any generic text editing method can be applied to grammatical error correction, but it has been shown that task-specific modifications and tricks can help further improve performance on this task. We will now look into what specific modifications have been proposed. The most prominent modification is to introduce task-specific edit operations. And one useful set of edit operations to introduce is suffix-level operations, basically adding and replacing word suffixes in addition to adding and replacing words. For example, a text editing method called py introduces 58 suffix transformations that are learned from the training data. These suffix-level operations are less sparse compared to the word-level operations, which helps the model generalize. Alex will later touch upon this aspect again in the section on multilingual text editing models. A similar approach has been taken by Gector, which is a text editing method that has been introduced specifically for grammatical error correction. So Gector implements so-called G transformations, which are basically higher-level operations on the word level. These operations include, for instance, merging words on a hyphen, changing the capitalization of a word, or changing the word form. For instance, putting a verb into its third-person singular form. These operations also help the model generalize because they are less sparse. And in order to implement these operations, in particular changing the word form, one needs to rely on external linguistic resources, for instance, a verb conjugation dictionary. On the other end of the spectrum, we have a low-level approach, which has been proposed by Straka et al. This is to introduce character-level operations. For instance, replace third character from the end with V. And these operations can also be learned directly from the training data. A slightly different approach has been taken by Seq2Edits. Here, the set of edit operations remains the same and generic, but the model is additionally forced to predict the type of grammatical error. So there is a public toolkit called Errand that allows classifying the error types based on the source and the target text. It distinguishes between about 25 different main error types, which include spelling, punctuation, noun inflection, verb form, and so on. And it has been shown that forcing the model to predict the error type improves the performance on grammatical error correction in a variety of settings. Finally, I'd like to list some recipes that people have found useful when applying text editing to grammatical error correction, even though these recipes are not specific to this task. First, it has been shown that pre-training on synthetic data is generally useful. One can obtain synthetic pre-training data for grammatical error correction by simply perturbing the correct target sentences with random noise. Second recipe, iterative refinement. The idea here is to apply the model repeatedly to its own outputs. Intuitively, if the input sentence contains many errors, the model may only correct some of them in one go, but if we apply it repeatedly, we may arrive at the correct sentence in the end. Third recipe, model ensembling. As usual, the best performance on any task can be obtained by putting together an ensemble of models. And one way to do ensembling for text editing methods is to basically average the predicted tag probabilities, the tag probabilities predicted by individual models at the token level. Finally, people have been optimizing the performance on this task by exploring the precision recall trade-off. Specifically here, it means tweaking the probability of the model doing nothing or making no changes either at the token level or at the level of the entire sequence. This has been all for grammatical error correction. Next, Yue will talk about text editing methods applied to text simplification.
Hello everyone, this is Yue. In this section, I'll be discussing edit-based models for text simplification. Text simplification is a process of transforming a text into an equivalent which is simpler to understand by a target audience. For example, given an input sentence, last year I read the book that is authored by Jim. Text simplification process can transform it into Jen wrote a book, I read it last year. We can see multiple operations are involved in such transformation, such as word or phrase substitution. In this example, authored is replaced to wrote. We can also see sentence splitting are often involved for text simplification. When we're given a long and complex sentence, text simplification process can break it into multiple shorter and simpler sentences. Deletion is also often observed in text simplification. For example, here that is directly deleted in the output. Moreover, syntactic style transfer is also often used for text simplification. Usually, we can observe that the text simplification process will transform the passive voiced sentences into the active voiced sentences. We see here in this example, last year, as a constituent part in this parse tree is moved around to make the overall structure simpler. If we look at edit-based models for text simplification, it was originally proposed as an alternative to machine translation-based sequence-to-sequence models, which have a large degree of generation freedom. On the other hand, edit-based models can bound the number of edits so that we can make sure the output and the input are relatively similar. It has certain advantages in terms of controlled generation, and it performs competitive or getting SOTA results on public benchmarks. In addition, edit-based models has advantages in preserving facts, as pointed out in this ACL 2020 paper on fact-based text editing. We've seen more and more papers are reporting edit-based models on text simplification. In this tutorial, we're going to discuss four of the models: SL, Edit NTS, RM, and Felix. So usually these models for text simplification are using these three most popular benchmarks, Wiki Large, Wiki Small, and Newzilla. For these edit-based models, it's often compared to the state-of-the-art sequence-to-sequence models at the time. In terms of evaluation, for automatic evaluation, SARI proposed by Xu et al. In 2016 is often used to measure the similarity to both the input and the reference sentences. In addition, human evaluation are also often performed in these papers, where the judges are asked to rate the different to rate the output from different systems based on fluency. Adequacy usually means how much meaning are preserved from the input and the simplicity of the output sentence. So if we look at SL, it is a sequence labeling model proposed for text simplification based on editing. So it's the first neuron edit-based model on text simplification, and this model is heavily rely on heuristics and other modules for operations. In this paper, 5 operations are defined: delete, replace, move, add, and rewrite. So how to label these edit operations? The author actually used a word aligner, which is external model. So this aligner will just compare the input sentence versus the output sentence, and then align each of the words of the pair. And then for any tokens in the input which do not have alignments, these tokens are labeled as delete. And then for any tokens in the output which doesn't have an alignment, this is going to be labeled as add. And then if we see 2 words do align with each other, but they're different, this operation will be labeled as replace. In addition, based on this word alignments, the author also defined the rewrite operation, which is a special case of replace. So in the replace, we require the model to have like 1-to-1 mapping. And then in rewrite, it could be 1-to-n or n-to-1 mapping. In addition, if we see across a line happens in the alignments, this usually indicate that a move operation needs to be performed. So the author defines these 5 types of edit operations obtained based on the word aligner as silver labels. So we can see that delete, replace, move, add, and rewrite are defined this way. And then this neuron-based model is used to predict these edit operations. So it just like basically predict or classify each token into these 5 edit operations in addition to keep. So we can see that delete, replace, move, add, and rewrite. However, there are only 2 operations that can be executed in this paper due to the restrictions of available external modules to perform these edit operations. So if the model predict deletes, the input tokens will be directly deleted, and if a token is predicted as a replace, the model uses external simplification dictionary to do the actual replacement. And for the other operations predicted in this paper, the authors didn't have a solution yet for these operations. And we see that SL reports their result compared to a sequence-to-sequence model by human evaluations. They ask human judges to rate the output based on like whether it's fluent, so grammar, whether the grammar is good, or like meaning preservation and simplicity. We can see that SL compared to NTS, it does a bit worse in terms of fluency and meaning preservation. However, it does perform better in terms of simplicity. This work has inspired many sequential work on edit-based models for text simplification. So one of them is edit NTS proposed in 19. So this model is basically given the complex sentence and also the simple sentence. The model will, the authors propose to construct the edit labels by using the minimum edit distance. So this is a completely end-to-end model, doesn't require external modules or aligners. And we see that 3 edit operations are defined: add, delete, and keep, where the replace is actually achieved by a combination of delete operations and add operations. So similar to SL, rather than teaching the model to learn to generate simple sentences based on the complex sentences, this edit NTS model is also teaching the model to generate edit labels based on the complex sentence. In particular, the authors choose a neuron programmer interpreter to model this PZ given X. We can see basically at the time step T, to predict the edit labels, the model takes 4 inputs: the previous generated simplified tokens, the previously predicted edit operations, the word or the token that is currently being editing, and also the context from the encoder. If we look at this overview of the model, we see that when we are having a complex sentence, first the encoder will encode each of the tokens and get their representations. Afterwards, the model will initialize the programmer and the interpreter by a start token. Then the decoder will revisit each of the tokens in the input and then predict the edit operations by the programmer. Afterwards, the interpreter will take the input token and also this predicted edit operation to produce a simplified token. And we see that this process is autoregressive from left to right, where the process automatically ends after the model decides what to do with the last token in the sentence. If we look at the result of edit NTS, which is a completely end-to-end model versus the best sequence-to-sequence model at the time, DRESS, we see that in terms of SERI on all 3 datasets, it's actually doing better. And as we discussed, so this is a paper in 2019 where the subtokenization was just started to be popular. So at the time, the edit-based model compared to sequence-to-sequence model that has advantage do perform better in terms of preserving the facts or entities which are out of vocabularies. In addition, if we look at this fine-grained edit operations, we see that on different data set, the models learns different behaviors. For example, if we look at wiki-large, both of the models are doing less delete, but rather keep most of the tokens. So we see that compared to New Zealand and Wikismall, the models on wiki-large are doing less compression. And such compression, like how much we're doing compression, can be controlled by giving a different cost for each edit labels. So the next model I want to discuss is the iterative editing model proposed by Kumar et al. In ACL 2020. So we see that this model defines 4 edit types: remove, extraction, reordering, and substitution. So unlike the previous 2 models, which are autoregressively performing editing, this model actually do edit operations iteratively. We see that given an input sentence, the model will just directly localize where we want the model to perform edits, and then perform the edits there, getting a new sentence, and then iteratively do this process again. And overall, the model it's learned to optimize this score defined on equation 2 until So this gives a criteria to the model when to stop editing in this iterative process. So we see that the model basically trying to optimize the score with these 5 sub measures: fluency while preserving the real word, and simplicity. And also the shorter sentences are rewarded in addition to rewarding entity preservation and content preservation. So what's left is to decide when to stop this iterative editing process. So the authors defines this threshold for each operations. And then when we're having a new candidate sentence, so this is after editing versus the sentence before this editing. So the threshold of the score has to be greater than certain number in order for this iterative editing process to continue. If we look at the results on Mozilla, what's interesting is RM as unsupervised model compared to edit NTS, which is supervised model. In terms of SURI, it's actually performed very similar. So this is a very impressive as an unsupervised model. And we also see that this ANT-PAR model, despite it's doing better in SURI, we see that most of the gain are just from this model is more aggressively deleting tokens. The last model we'll be covering in this section is Felix flexible text editing model proposed by Mellison et al. In 2020. So similarly, this model is also predicting the edit operations. However, it uses this two-step approach. So the tagging model basically predict the edit operations, and then the insertion model will decide what tokens to be used for replacement or for adding. And compared to sequence-to-sequence models, Felix requires less training data, so that it's more sample efficient, and it's also faster in inference time, as we can just tackle a particular area in the input. This is also provide more flexible text editing compared to other models. If we look at the result of Felix compared to the sequence-to-sequence model NTS, it does perform better in terms of SURI. Also, Felix is performing better compared to edit NTS model. We can see that there is also a small performance gain here. So next, I will pass the floor to Eric to discuss the text style transfer with the edit-based models.
Thanks, Yue. So next we're going to talk about text style transfer. And what makes this problem interesting, also from the text editing point of view, is that usually this task is addressed in an unsupervised manner or with only using non-parallel data. So the question is, how do we train text editing models when we don't have any parallel examples? And another way to contextualize this work is that, and actually what led us to think about this problem was that we had seen how effective pre-training is also for text editing and not just generic sequence models. So we saw this first of all with LaserTagger, and also Seq2 used pre-trained encoders, something like BERT. Then later with Felix and as well as Edit5, we've seen that if you also have a pre-trained insertion model, it guarantees you to get more natural outputs and better insertions. But then the one remaining question was that how could you also train the tagger? Because that's not, I mean, you have pre-trained encodings, but kind of the softmax layer on the top that decides which stack or edit operation to apply, that is not pre-trained. So this led us to develop a method called Masker, and in this section I'll also present a method called Lewis, developed by some other people. So, but first of all, what is the task? So in style transfer, you're given only non-parallel data, both from the source and from the target domain. And then your task is to transfer a source sentence into the target style. So for example, in the case of sentiment transfer, you would transfer a sentence like the best place I've visited into a target domain, something like the worst place I've visited. And a very common approach in academia is to decompose this task into two subproblems. First being determine the words to be deleted, and second, determine how to replace the deleted tokens. And this is also the approach that both of the methods discussed here, namely Lewis and Masker, follow. But so to start with the Masker, our idea was to leverage BERT-style masked language models. And before I present the full Masker approach, let's consider a slightly simplified approach. So something that seems kind of reasonable that one could do would be to take a masked language model, train it on the target data, then mask out each word one by one, and compute what is the likelihood of this word under this target domain model. And then for all the low likelihood words, you would replace them with something more likely according to the masked language model. So you could hope that this would bring the sentences closer to the target domain. Okay, so let's see how this would work with one example. So if you consider a sentiment transfer going from negative to positive reviews, so you could have a source sentence like price isn't bad while food is the worst in Zurich. Okay, so let's start from the first word. Price probably would get fairly high likelihood, isn't as well. Bad is an interesting case because it's a negative word on its own, but given that the model is contextual, it should figure out that given the negation, it should also get high likelihood. However, once you go forward, then you get to the word worst, and this would probably get a very low likelihood given that the target model has only been trained on positive reviews. Okay, so this would be a sign that this should be replaced, and the model could output something like best as the most likely insertion for when you mask this out. Okay, and this is exactly what we'd like to see. But then the interesting case happens when we go to the last word, in Zurich. So here, actually, if you think about it, it could be talking about any place, and any particular place would probably have a very low likelihood. So the model would very likely end up assigning very low likelihood for this particular entity as well. And as a result, it would end up replacing this with whatever popular city or place happens to get the highest likelihood, which is clearly not what we want because it's not helping us to transfer the sentiment any closer to the target domain. So the solution we proposed in Masker was to consider not only the target masked language model, but also train a masked language model on the source domain. And then you can compute the likelihood under both of these models. So for this particular word, also the source model would say that, yeah, this doesn't look likely. Whereas if you consider the word worst, here on the other hand, the source model would be very happy. Yeah, this looks exactly like what I'd expect to see here, given that I've been trained on negative reviews. So the key here is that whenever the two models disagree, this is a sign that here probably one should change something. So this is how we leverage these two masked language model to kind of get signal for the tagging component of text editing. And we use this not only on its own, but also as a pre-training approach for other text editing methods. So you can imagine that this is not very fast. I mean, you can parallelize it, but it's still quite expensive to compute this over all possible words or even all possible n-grams like we did. But we can use this to create silver data to pre-train a much more efficient model. And here are some results, not on style transfer, but actually on sentence fusion, which we've discussed earlier. So if you use, if you train LaserTagger on very low resource setting or zero-shot setting, plus you add some silver data generated by Masker, you get very clear, significant improvements from having this silver data. And this applies both, we tried it with LaserTagger, also with Felix, one variant of Felix, as well as Seq2Edits models, and this always helped. Okay, and I will later show you some results on style transfer, but first let's go to the other method I mentioned. So this is called Lewis by Wright and Chong from 2021. And first of all, the tagging model architecture or the text editing architecture is kind of similar to something we've seen before. So first, you have the tagging or the encoder, which in this case is a Roberta model, which predicts operations like insert, keep, replace, delete, and so on. And then you create another input for a separate insertion component, similar to what we've seen, for example, in Felix. And then the insertion component, which in this case is an autoregressive BART model, fills in these mask tokens. Okay, but so here the question still remains, how do you do this in a non-parallel setting where you don't have initially any training data? So the approach that this paper proposes, which is similar to some of the other works in the style transfer, is to use style classifiers and attention mechanism. So first you train a style classifier to distinguish between the source domain and the target domain examples, then use the attention scores of individual words or phrases, and you hide out words that have high attention scores. And this gives you some parallel data, and then you can train this model I showed you on the previous slide. Okay, right. But so more specifically, how do you generate this parallel data? So, right. So you take a sentence, then you run it through this style classifier. You take the words or the spans which get high attention scores. You mask these out, and then you fill these masks with the mask language model trained both on the source model and on the target model. And this gives you two different variants of this style agnostic template. And then you can use these two synthetic variants as a training example. Okay, some results showing also results from our work. So here, what you can see that quite interestingly, well, first of all, doing this with Roberta and BART and supporting multiple insertions rather than just single, what we did with Masker, gives you clear improvements across the different scores. Another interesting finding, which we also saw with the Masker paper, was that if you, instead of than using the Masker directly, you label the examples with Masker, then you train a model and rerun the model on the exactly same examples which it was trained on, it actually interestingly improves the results. So this kind of form of self-training or of distilling Masker into LaserTagger. And similarly also with Lewis, when you combine the data with LaserTagger, you get pretty nice improvements. So you can see that you can view LaserTagger as a way of regularizing the outputs. So this limited phrase vocabulary ensures that the craziest sort of generations by the mask language model get filtered out, and you just get the most common ones, which seems to, on average, improve the results. Okay, so with this, I'll hand it over to Sebastian, who's going to talk about incomplete utterance rewriting.
The next application that we talk about is called incomplete utterance rewriting. This task is best understood by looking at a real-world example. What you can see on the slide is a video from a recent Google AI blog post about the query understanding component inside of the Google Assistant. The video shows a concrete multi-turn interaction between a user and the Google Assistant. At the top of the screen, you can see the user's queries as they are recognized when the user speaks. And based on these user queries and on what the assistant understands of them, an answer is displayed. The thing to note here is that all but the first user query are semantically incomplete. So the user is leaving out key information that is important for the assistant to have. And the user is implicitly or explicitly referring to the past dialogue turns. Now the critical assistant component that jumps in here rewrites the user utterances into a complete and standalone form. And this complete and standalone form then makes it easier for the assistant to provide an answer. And yeah, that's the task of incomplete utterance rewriting. So utterance here in the task name just refers to a user query. By the way, what you can sometimes see pop up at the bottom of the display are suggestions for follow-up questions that the user can select, but the user doesn't have to. So this is actually independent of the task of utterance rewriting. Let us formalize that a bit. The general setting is that we have an open domain dialog between the user and an agent. And what we want to do is to rewrite the most recent user utterance, which is incomplete, into something semantically complete. In other words, we want to reformulate conversational queries into natural but standalone and human understandable queries. There are alternative task names used in literature, and they reflect this definition. So sometimes this task is called conversational query rewriting. Sometimes the task is called question in context rewriting. But all of these names refer to the same task or to at least flavors of the same task. Now this slide has another example dialog. We have a user who asks, why did Federer withdraw from the tournament? Then the agent gets back and answers, well, he injured his back in yesterday's match. And then the user has a follow-up question, which is, did he have any other injuries? And the concrete issues or problems that the assistant has to solve here in understanding this are two in this example. So first, in the purple box, the agent has to resolve this pronoun to something in the context. So he has to be resolved to Federer, and then also this ellipsis in the end. There's this condition from the context that he hurt his back, and that is also relevant and should probably occur in the user query or in the rewritten form. And what you can see at the bottom then is the standalone version. Did Federer have any other injuries besides his back? And that is something that can very well be addressed by some answer seeking component. Okay, so what the previous example showed is that the natural way to tackle this task is to process the user utterance to be rewritten word by word, and to decide for each word whether to keep it or whether to delete it, and also whether to insert some phrase from dialogue context. A key characteristic of this task is that most insertions really happen from the previous dialogue context, either by resolving implicit or by resolving explicit references. So this task is really an ideal application for text editing methods, which is why we talk about it. And this characteristic of this task can also be seen in the approaches that are used in published papers on this task. So while a frequent approach in the last 5 years is definitely to use a vanilla sequence-to-sequence model or to use a decoder-only language model, many papers add on top some form of text editing idea, some improvement that is going into the direction of text editing. And these are the papers that you can see here in the middle column on this slide. For instance, what they can add is a copy mechanism that the model can decide to use instead of generating something from scratch, something from a large unbounded vocabulary. Another example, what can be added on top of a vanilla sequence-to-sequence model is just that some words from the input are highlighted in order to bias the model towards regenerating them. So basically just to emphasize that these words are probably very important. And then more recently, we have a lot of pure text editing papers, and that's the rightmost column on this slide. And we are going to look a bit more into the details of one particular approach, that is the approach by Jin and others, published this year. So this approach, this paper is called Hierarchical Context Tagging for Utterance Rewriting. And there are two characteristic properties of this approach that I would like to highlight. The first one is that this approach supports reordering of input text, of input words. This is not supported by all text editing methods that were published in the recent years. And the second one is that it is possible to insert words from a limited vocabulary of common words. And this vocabulary of common words is built as part of the training process of the model, actually, as part of a pre-processing step before the actual model training commences. What this slide shows you are examples of the so-called slotted rules that this approach is built on. And these slotted rules have fixed lexical elements in them, like by, then, aside from, etc. And these fixed lexical elements, these terms, do not need to appear in the context, and still they can be inserted by the model. Let's walk through this approach together to make it clear how it generally works and how these slotted rules are used. The first step is that the dialog context and the last user utterance are concatenated. This is represented by the gray box at the bottom of this slide. This text is then encoded by BERT here in this instance, and then the later parts of the model have access to that calculated representation of the context and the last utterance. And well, this representation is used by the following steps, which run partially in parallel and partially in sequential order. Highlighted on this slide is the tagging step that produces the keep and delete edit operations for every input token of the last user utterance. Then in parallel, for each token in this last user utterance, a slotted rule is predicted that is inserted before each token. So the slotted rules, this is what was shown on the previous slide. And as I mentioned, they are calculated in an offline step before the training, and they determine two things. So they have two elements. One, they determine how many words from the context of the dialogue should be inserted before a particular token. And then second, they determine which fixed lexical terms should be inserted as well. And these fixed lexical terms would be prepositions or determiners or things like that. So things to make basically the whole rewrite more grammatical. And then the fourth component is the span predictor, which is an encoder-decoder component that processes the selected rules from the rule tagger component. For this, the slotted rules are converted to text by inserting special mask tokens. And this is then ingested by the encoder, and then the decoder predicts for each mask token a pair of indices that point into the dialog context and that determine which words from dialog context should be inserted in a particular position of the last user utterance. Okay, let's take a step back and look at the particular issue and risk that generation models are associated with. And that issue are hallucinations. Now, text editing models have a different risk profile compared to models that generate from scratch. And in this part of the tutorial, we will look into that and then also see particular ways to lower the generation risk of text editing models. So what are hallucinations? Let's define them as a part of generated text that is either nonsensical or inconsistent with the provided input text. There's a growing body of research on this topic. Here we follow the taxonomy from G and others. In literature, another related term frequently pops up, and that term is factuality. Factuality is the quality of a statement, a generated statement that is, being true or being based in a fact. Now, there are two general variants of hallucinations. The first one are those where just by looking at the input text, it is clear that the generated text is factually incorrect. And the second kind are those examples where the generated text is basically adding information, and that added information can be true, it can be false. We don't know without looking at additional information sources. And the thing here is that because this is a model that adds this information, we do not want to be in a position where we have to trust what the model generates. So this is why it's bad. Even though it can be true, and even when it is true what the model inserts, we might not want to have that. Let's look at an example. So this is a modified version of the earlier example from incomplete utterance rewriting. At the bottom of the table, we have the model output, which contains, in this case, two hallucinations. The purple box shows an example of the latter hallucination kind. That is, the model inserts the given name Roger here. This happens to be correct. So Roger Federer is actually the name of a tennis player, but it is still undesirable for the reasons that I've just explained. So it's not grounded in the input text, so we do not want that. And the orange box is an example of the earlier hallucination kind, where the information in the generation can easily be identified as contradicting the earlier conversation context. That is, he hurt his back and not his leg. Okay, so what are causes of hallucinations in models? A major source is training data, specifically the divergence of source texts and references in training data. This can happen when data items are automatically constructed. For example, there's this academic task of data to text generation. And what researchers do there is they align different data sources to produce the training data. And that so these different data sources can be text from a specific Wikipedia article that is aligned then with that article's info box. And while generally the information will be the same in the info box and in the Wikipedia article, it's not clear that every data item that you generate out of that is really 100% aligned. And it's just very easy to introduce noisy training examples when doing this in an automated fashion. And then if the model is trained to introduce new terms and to hallucinate, then this is just what the model will do at inference time. Another cause of hallucinations is world knowledge inside of the model. And more of this world knowledge is available in modern day generation models. So the larger the models get, the more information they keep from training. They keep from what was mentioned in the source texts. For instance, information about the given names of sports personalities, as we have seen in the example in the previous slide. Third cause can generally be described as model quality issues. So these can be imperfect representations obtained from an undertrained encoder, or the choice of a wrong decoding strategy. wrong in the sense that if you pick a strategy like top K sampling that encourages variety of output, you will just get more hallucinations naturally. Now, all of these causes affect text editing models just as much as they affect text generation models. But in text editing models, we have some natural ways to mitigate hallucinations. And let's look at these. So what are the concrete advantages that text editing models have over text generation models on the hallucination front? 3 aspects come to mind here. A, tokens from the input are heavily reused. B, if we decide to not reuse a token, but to insert a new one, we often do so from a small vocabulary, and that small vocabulary might even be hot fixable. And then C, we can design custom edit operations for critical use cases. Let's go over these aspects in order. So to aid the reusing of input tokens, why does that reduce hallucination risk? Well, any token not generated from scratch is basically a token that is safe from hallucination. And while there are text editing models that are that partially generate from scratch from an unbounded vocabulary, the general statement holds for these kinds of models as well. So as a concrete example, imagine there is a text editing model that is employed for utterance rewriting in an actual user-facing physical product, such as the smart display that we saw earlier. Now, if you as an engineer want to understand the risk that comes with having this text editing model showing output to users, what you would do is to analyze for a large representative sample of data how often the model actually inserts a word versus decides to keep something from the input. And say you would be relieved to find that in 3/4 of the time, 3/4 of the input utterances, it completely just copies words from the input over and maybe does some deletions, but does not insert new words. And this would also be a really nice metric to automatically monitor to see if maybe the behavior of the model shifts over time as the conversation topics that users go for change. Now, this is something that text generation models do not provide to you that easily. So to the second point, here are a few examples where we can see different error types that models, both text editing models and vanilla text generation models, can suffer from. So we have the generation of imaginary words, we have repeated phrases in the output, we have in general just hallucinations, we have issues with coreference resolution, etc. And the second and third column show you for LaserTagger, which is a text editing model, and for a BERT-based sequence-to-sequence model, if these two models are affected by the respective error kind. And yeah, so LaserTagger is a text editing method that has a restricted vocabulary from which it inserts. So this is a particularly safe model from the hallucination point of view. And this is shown here in this table by the few error categories that LaserTagger is potentially affected by. At least the fewer categories compared to vanilla sequence-to-sequence models. And the advantage of working with a fixed small vocabulary, as LaserTagger is doing, is that it is easy to produce hot fixes by just removing entries from this restricted small vocabulary without hurting the overall quality of the model too much or maybe at all. So here's a made-up example on this point, again for the utterance rewriting task. Imagine the training data of our Utterance rewriting model is sourced from actual queries from US users, and that this data was collected in a particular and restricted time span. Now, the model will pick up on all sorts of accidental patterns and correlations in training data. Some of these might surface right away, that is during an evaluation of the model, and then they can be handled. But some of these might only do so over time after having deployed that model into production. What you can do if an error surfaces after deployment into production is that you can hotfix the vocabulary and therefore surgically alter the inference time behavior of the model. Let's look at this example. So here the training data of the model was from the time when Barack Obama was US president, and like in this example, the training data was only from that time. So the model has learned a really strong correlation between a reference to the president and Barack Obama. And in the first row, this is actually fine. How old is the president? Does he have a partner? There, he really refers to Barack Obama, so the rewrite of the model is fine. In the second case, however, the user is talking about the president of France, and rewriting this to Barack Obama is not correct. So this could easily be fixed by just modifying the vocabulary to not contain the concrete entity name Barack Obama anymore. And then the third example is going even a little bit further. There, the correlation might even be that the concrete person is just associated with a specific pronoun. So here again, Barack Obama with he, and in that case, the problem would even be bigger and it would surface even more often. And you can also fix it with by modifying the vocabulary. Okay, the third advantage of text editing models over text generation ones is that we can easily account for particularly sensitive use cases. One such use case is bias in natural language generation. This is a very active research area. You can see an overview of studies on this topic on the slide. And some of these studies are even looking into bias for text editing. I think here it's called rewriting. So one way that bias can surface in natural language generation is that male pronouns can be preferred by a model in the sense that they are more likely to be produced, they are more frequent. This bias would come from training data, and text editing models can be affected by that as well. But with text editing models, we have an easy way to mitigate. So imagine we are working on a model that is supposed to do a pronominalization as part of its main task. What we can do is we can introduce an additional edit operation. So in addition to keep, delete, and insert, we can have an operation for pronominalization. And then the model is freed from the decision making of picking a gender for a pronoun to insert. So instead of inserting he or she, his or her, it would just predict this pronominal tag. And then in a post-processing step, we would do in a database grounded way this gender lookup. Basically, we would look up the preferred gender of a person. And this is really safe. And in this concrete example here on the slide, we would free the model from having to guess Alan Turing's gender. Yeah, and this is just a really nice property of a model to have when you are running it in a really critical environment. Okay, let's talk about another particular way to leverage text editing for safe and controlled generation of language. And that way is to bias certain types of edit operations in the model with the effect that potentially dangerous edit kinds will happen more or less frequently. This has been used quite a bit in literature. The first paper on the slide worked with a boost for the probability of the keep operation. That way the model was more inclined to leave the input text unchanged. And well, the idea in the second paper is a similar one. And the third paper had control knobs for each of the three high-level kinds of edits: keep, delete, and insert. Let me show you a chart from this paper. What you can see here is the effect of increasing the bias of the three kinds of edit operations individually. The blue columns correspond to a setting where the insertions were heavily encouraged. The red columns represent a configuration where the model was biased towards predicting a keep tag for most tokens, and the yellow columns are from a setting where delete tags were encouraged. Now, the leftmost group of columns shows that the average length of generated texts got longer when insertions were encouraged and was reduced when deletions were favored. And this is what you would expect. The middle group shows the percentage of copied tokens from the input, and biasing the keep operation, like putting a higher bias on the keep operation, results in the largest fraction of retained tokens. And the last group shows that rewarding insertions really has the intended effect of letting the model produce more novel words when compared to the words in the input stream. So what this chart shows you is that biasing of edit types is a really easy way and then also effective way to influence text editing models' behavior. Next, Felix will talk about controllable dataset generation.
Most of the use cases for edit-based models we have seen so far employ the models directly to solve a particular NLP task. In this section, I'll talk about a different use case in which edit-based models can help training a regular sequence-to-sequence model through synthetic training data generation. So, synthetic data generation is an important building block for many sequence-to-sequence models nowadays. Back translation is still one of the most effective ways to use monolingual target language data for machine translation. Back translation in MT uses a reverse translation system to translate the target language text back into the source language, which is then used to train the main machine translation system on the synthetic source to target language pairs. Applying the same idea to other text-to-text problems like GEC would mean that instead of a reverse translation model, we would now need a corruption model that introduces grammatical errors into clean text in order to generate the synthetic training corpus. It turns out that this does not work very well for grammatical error correction. A simple sequence-to-sequence corruption model that is trained on the reversed GEC corpus, mapping from the corrected sentence to the incorrect one, does not always generate realistic data. The output is often not very diverse, and it tends to synthesize only trivial errors like simple punctuation errors. So the question now is, can we use error type tags, for example, the ones provided by Arendt, that are also used in Seq2Edits to generate more diverse and more realistic grammatical errors? Such a tagged corruption model would, in addition to the input sentence, "there were a lot of sheep," take a specific error type tag, such as noun inflection error, as input, and corrupt the input sentence in that particular way. In this case, the noun inflection error is introduced by replacing the word sheep with the incorrect plural form sheeps. If we had such a tagged corruption model, we could use it in the following way. We first extract the unigram distribution over error type tags from the GEC development set. Then we take a large collection of clean English sentences, for example the SEO4 corpus, and corrupt them with a tag corruption model to generate the synthetic parallel data for GEC. We assign error type tags to the clean to be corrupted C4 sentences by following the development set tag distribution to create training data with the same distribution over errors as the development set. The only remaining question now is, how do we train a text corruption model that takes both an error type tag and a clean sentence as input? We explored two different options. The first option is to simply prepend the desired error type tag to the input and then generate the corrupted sentence with either an edit-based or a full sequence model. If you use a text edit-based model that uses the error type tags in one of its output tapes, it is also possible to instead constrain the corruption model using finite state transducers such that the output has to pass through the desired error type tag. So it turns out that text edit-based corruption models are much more effective in synthesizing useful GEC training data than text full sequence corruption models. Tagging the input with error type tags actually hurts full sequence corruption models. But Seq2Edits integrates the prediction of span level error type tags directly in the model architecture. So it can condition on the desired corruption tag much more naturally and generate useful GEC training data with both options, option 1 and option 2 from the previous slide. Tag corruption is also useful to adapt a GEC system to the proficiency level of the user. In this experiment, we divided the BRDEF set into 8 parts, 2 for each proficiency level, CF, R, A, B, C, and native speakers. We used one part to extract the tag distribution for the corruption model to match, and the second part to evaluate the system. It turned out that although the method was not very effective to discriminate between different CFR proficiency levels, it was very effective to adapt the GEC system to native speakers. For general purpose GEC, we found that both the BRDEF distribution and also the uniform tag distribution generalize well across many GEC test sets. A 200 million GEC training set that was generated using a Seq2Edits corruption model matching the BRDEF tag distribution is available on GitHub under this URL. And we found that it is very useful to pre-train GEC systems. Now, Alexander will tell you more about efforts to train multilingual edit-based systems.
Hi, I'm Alex, and I'm going to talk about the multilingual text editing. So we're going to start with tokenization. So tokenization is something that you have to do, but some people perceive it as somewhat boring. Like you just need to, write some code to process your text, but it actually is important because this is how the model sees your text. The model doesn't know about words or even characters. What it sees is the tokens that you supply to it. And why is it important? Well, it's mostly important for practical applications. If you notice that the model is doing something wrong and you trace it back to a wrong tokenization, then most likely you have to rerun the training of your model. And this is going to be costly and time-consuming. And tokenization is particularly important to get right when you work with non-English languages. And we'll see a bit more of that very shortly. So just a very high-level overview, there are different levels of tokenization. So the simplest is that you start just split by words. And there is subwords, morphemes, so linguistically motivated segmentation of words. And on the lowest level, there is the character or byte tokenization, which we're going to talk about in a moment. And one can notice that the original LaserTagger paper used the word tokenization, whereas Edit5 and Felix papers used subwords. So these are the models that we've discussed before. But this is just an implementation detail. You can actually easily swap the tokenizer that the model is using, and it may work better or worse for a given application. And the application is more important. So for tasks like sentence fusion, it's probably beneficial to work on the full words level, at least for languages that are similar to English. For other applications, you might want to do something else. And to give an example, we can consider these two extremes. So one is the word level tokenization, where we just split text by white space and punctuation characters. And on the other side, we have the character level tokenization. So you can pause for a second and think what are the issues and pros and cons of each of this approach. But basically, the main disadvantage of using the word-level tokenization is that it doesn't handle morphology. As we'll see later, like most applications, like even in English, but more so in other languages and more so for some applications, will need to handle the morphology. And if you work with full words, this is tricky. On the character level, the biggest issue for the text editing approach, especially if you use the non-autoregressive decoding, then since the tokens are produced independently, in this case the characters are produced independently, it's very likely that the model will generate something nonsensical, and we've seen that happening in practice. Okay, so we talked about the issues for text editing, but there are some issues that come up for any application, whatever you do. Like you first start with tokenization, and then you do like either your Seq2Seq or the text editing model. It doesn't matter. This will be your problems. And the main one for the word base is that you are going to see the unknown words. So some words that you have not seen during pre-training your model, and this is a big issue because you don't know what to do with these words. You don't know how to handle them. Even if you don't have this issue so often, there's still a very large vocabulary that you need to cover. Like there are so many different words even in English, but more so in highly inflected languages like Turkish, for instance. And this is going to be a problem because your training data will be sparse, your embedding matrix will be big, and these rare words are somewhat tricky. On the character side, okay, you don't have rare words, you just have a very limited number of characters, but on the flip side, what you get is they have a very long sequence. So the model has to encode a very long thing and emit a lot of sequence of big length. And this is potentially leading to lower quality. And not just lower quality, but it's also slower inference, slower training, and not great. And potentially an issue is that the model is operating with this characters or bytes, even if you want to go to the lowest level, which are not necessarily meaningful for the languages that you're dealing with. So like some languages use multiple bytes to encode the characters, and one byte just doesn't have an inherent meaning. I mean, that may not be a problem. The models are usually good at figuring that out, but just something to keep in mind. And there were several papers that used character level or byte level tokenization in the Seq2Seq approach. I think we haven't come across those that used it for text editing, but as I mentioned before, like swapping a tokenizer in text editing model is very easy, and by all means, go ahead and try that. Something in the middle between the word tokenization and the character tokenization is the subword segmentation. So here is an example of the sentence piece implementation that splits this text as this. So this is something that is learned from the data, so it's usually optimized using some kind of algorithm like DPE, UniGramLM, or WordPiece. And then this is your vocabulary, and it has some properties which may or may not work for your application. And what's interesting is that if your task is to generate text, it's important that this tokenization is reversible. And many pre-tokenized text found in academic tasks, they are not like that, especially in English. Well, English is easy again, but if you consider French, for instance, in French, before a semicolon, you put a small space. And if your tokenizer just strips spaces around the punctuation symbols, you don't necessarily know where it has to be inserted. So you can write a lot of custom logic for that, but that's not great. So sentence piece is nice in that case, in that sense, is that preserves the position of the white spaces. And yeah, just a note that the typical vocabulary size that people are working with is somewhere from 30 to 250 characters. And again, like if you're dealing with more languages in the single vocabulary, you probably want a bigger vocabulary, but yeah, like it should not go too big. Usually that doesn't make sense, it's even hurting the performance. Okay, so I just want to give a shout out for this great paper that shows an overview of the tokenizer. So the pictures, it's just a nice one. I don't want you to read it all in detail. Read this paper called Between Word and Characters. It's very useful to understand the landscape of the different tokenizers and what their pros and contra are. One thing to watch out though is that the paper doesn't have a focus on generation. So text editing is a kind of natural language generation task. And what may work for things like classification, so for instance, they don't talk about this problem of unknown character that we're going to talk about next. This, like for things like sentiment classification, it's not such a big issue as when you need to generate text. So just bear that in mind, that the paper doesn't have all the answers. Okay, so now we're going to talk again about the different languages, and this is just an illustration to show you that even the basic thing like alphabet is not necessarily understood the same in different languages. So if you work with ASCII-based languages like English, German, French, Indonesian, then you are dealing with something less than 100 different characters. If you work with Cyrillic languages, it's already twice as much. And if you go to Korean, then the alphabet characters, I know that that's not how Korean people normally treat it, but you can, like, as the way we encode it in the UTF-8, there is actually over 11,000 different characters. So that may be an issue. And why is it an issue? So consider the following example. So as we know that the subword algorithm, so when we optimize what things end up in our vocabulary and what things do not end up in our vocabulary, it's a greedy algorithm, right? So if the word dog appears more frequently than the word subword say or this character, we'll probably have the word dog in our vocabulary, and these two are less likely to get in there. And now, what do we do if we need to encode the word sensei? So we have sen in our vocabulary, probably because it's more common. Let's just assume we have it, but say we don't have. So, well, that's not an issue because, I mean, English is just ASCII, so less than 100 different characters are used there. And we probably have these individual characters in the vocabulary, so we can just encode it. It's not ideal, but still we've successfully encoded this word. And if you have the same word in Korean, well, I don't know how to read it, probably something similar. The issue is that the first character, well, it's frequent enough, we have it in the vocabulary, but the second one we don't. It's not very frequent, it's used in this word, maybe a few others, so it didn't make it to the vocabulary. And this is an issue because now it's an unknown character, and the models don't know how to deal with it. Like, they cannot even emit this because, like, they can only emit most setups only things from the vocabulary. They can try to, like, work it around with, like, just copying it by default if it's a known character, but that's not ideal. A somewhat better approach, which is used by the sentence piece model, and is to fall back to bytes. If the character is unknown, we can just encode it as a sequence of bytes, and that kind of solves the problem. So yeah, just something to keep in mind, because it's a real issue when you work with, especially with alphabets like Korean, Chinese, or Japanese. Okay, now we're going to talk more about the problems that is more specific to text editing. So this encoding of unknown characters, you'll get it for Seq2Seq as well, but for text editing, what you probably want to pay more attention to is the morphology. And this is the example that we've considered before for the grammar correction task. And you see that you need to drop some words and insert some words, but what you notice is that, like, this replacement of drives by drive is potentially inefficient. So your model needs to drop the whole word and insert the new word, and it may or may not be able to figure out that these words are related. And a better approach would be to have a model to treat it specially. And as you know, the one advantage of these text editing models is that you can introduce arbitrary tags. So for instance, you can say that, okay, we have a special tag that we apply to the token that is the conversion of the verb form from the third person singular to the third person plural. And it's going to handle things like drives to drive, goes to go, carries to carry, which probably someone's already implemented somewhere in some tokenizers, and you can just piggyback on that. Or if you're a big company doing grammar correction like Grammarly, so this is a screenshot from their paper, you can implement a whole bunch of things in a whole bunch of languages. So you don't have to read this in detail, but basically there are all kinds of different replacements, and there's a lot of code behind this that does this conversion. And that works well because they have all the control that you need, but that's somewhat tiresome to implement. So an idea is that why don't we just infer it from the data? So instead of learning the vocabulary of word replacement, you remember this algorithm that we've used, a sequence alignment, when we have input tokens and target tokens, and we want to find the best alignment between them so that we can have the most efficient tag representation. We can do something similar on the character level. So we don't discard the tokenization that we have, as I'll show you later, but just for the editing operation, we are going to look at the character, like descend to the character level, so that we could support the morphological edits. And instead of tags like this, so this again from the example that we've seen before, well, this is actually working well for things like sentence fusion, just inserting the whole word or words or dropping the whole words. Instead, we can have the vocabulary where we just append a single character, or we replace a character at a given position, or we uppercase it. Just to give an illustration, let's say that we have this sequence as input. We first tokenize it. So again, here we don't do the character-based tokenization. We tokenize it, it gives us 4 tokens, for instance, and then to get the target sequence from it, we are actually having the tokens applied to this individual tags applies to these individual tokens, and here, yeah, we have the uppercase second character. So we take this token, gather. It starts with a white space, so the second token would be uppercase. So we'll get it gathering. Then the second token are IN. The tag is append G, so we get ring. Then this token we just apply keep, so it stays the same. And finally, for the last token, we apply this tag that tells us to replace the first character by the letter V. And you can look at this paper for more detail, but basically, like, you don't need to engineer lots of this replacement. You just let it infer from the data, and this is great because it can fix things like typos, as you see here, or morphological edits. And this is especially important for morphologically rich languages, like most Slavic languages are, for instance, or the languages like Turkish, which use a lot of suffixes, things like that. Okay. Right, and before we go to the whole tutorial section dedicated to the practical aspects, just a sneak peek that is specifically for multilingual aspects. We're going to talk about 2 things. So one is the question of whether we have the per language model or a single multilingual model. And both of them has some pros and contra. So if you have a per language model, you can get one with a very efficient dedicated vocabulary. So for instance, there's a Korean bird or Russian bird that you can base your model off of. And the main benefits there is that they have a dedicated, like separate vocabulary, separate word piece or sentence piece vocabulary, and therefore you get a better performance. Potentially get smaller models. So if the models are only handling languages that you care about, if it's not a lot, then maybe you don't want to start with a multilingual bird checkpoint or T5. And then the last one is very important actually for practical application, is the release cycle. So let's say that you made an update to your model in, I don't know, Thai, and or Indonesian, and you don't want to make sure that it, like you do, but if the models are independent, you don't have to check that this model still works well for, say, French or Arabic, because these are independent and you can just release them. On the other side, for the multilingual, single multilingual model, you can potentially get some benefit from other languages. You have more like higher resource languages, and then the model is able to generalize from them. Your training pipeline is simpler. Like if you're dealing with 10 or 20 different languages, even especially if you're dealing with 100 languages, like training 100 models is probably a bit more involved. And potentially you have lower maintenance costs. Again, this is the very practical thing. So you don't have to like set up monitoring for 10 different models or 100 different models. You don't need to like babysit them when you release and make sure they work. You just have one model and have a single unified monitoring. And potentially it's also a lower resource footprint. Like if you just have one model running all the time and serving dozens of languages, then it's more efficient. And this is just an illustration. This is a simple experiment that we've done. One could still have a single model because they have all the advantages, but separate the output, the tagging vocabulary. So the English model will have the tag insert end, and then the German model will have insert und, because this is different word for end. So things like that, and you can have it in one flat vocabulary, but that means that you need to do a softmax layer over all of this. So if we're talking about LaserTagger, so this was experiment performed on LaserTagger, and there you see, like with this change where we have just a single, we have separate vocabularies per language, the performance stays flat. So this is the inference time, depending on the number of languages. Whereas if you go for the unified vocabulary, so I guess it depends on which languages you have, but it kind of grows linearly. So the more languages you have, the slower your model is. So that's something to keep in mind. And okay, I'm going to finish it with this idea that one size doesn't fit all. So if you work with depending on the applications that you are working with or the languages that you support, you may want to have like let's say smaller or bigger vocabulary, and that means that you need to see. And like bigger, let's say sentence piece vocabulary means that you have smaller sequence length than we've seen before, so faster encoding. But then the alignment between source and target potentially is suffering, like as we saw this drives versus drive. This is not necessarily, if your sentence piece already separates this, then the alignment works better. The model becomes bigger if you have a bigger vocabulary, and so you need to experiment. It may be that for your application, bigger vocabulary is better and the smaller is not. And more importantly here for multilingual aspects is that the different languages needs to be treated differently. As we saw for Korean, you probably need to allocate a bigger portion of your sentence piece vocabulary to Korean, so that you can have the words like sensei natively supported. And it's a bit of an art to find the optimal split between them. Like, so you have to experiment or run some kind of hyperparameter tuning, but that's a bit too much if you need to like optimize between different languages. But yeah, you can try. There's also this paper that talks about training multilingual vocabulary and joining them. It's a bit too involved to my taste. I think just allocating a separate half of your vocabulary or a third of your vocabulary or a quarter of your vocabulary to languages with bigger alphabets like Korean or Japanese or Chinese, it's probably going to work just as well, but much simpler. But yeah, if you're fancy, you can do the fancy things for this paper. Right, and with that, I'm going to pass it to Jakub, who will tell you more ideas about the productionization of the text editing models.
Thanks, Alex. I wanted to talk about a few aspects of the productionization of text editing models. So let's return to this slide from the beginning, where we discussed the advantages of using text editing models. Two of these advantages we've discussed in this talk so far. So one is faithfulness, and the other is greater control over your outputs. Two aspects that we haven't discussed as much are the latency of text editing models and their data efficiency. So I'd like to start by discussing latency. I wanted to show you a case study in how a text editing model, specifically edit5, can be faster than a T5 model. What I did is I trained these two models to do grammatical error correction, and I ran them on the same input on a GPU, while capturing the computations that the models were running. So we will be looking at these computations in detail in the TensorFlow profiler, but if you're a PyTorch user, you should know that it has similar tools. Let's take a look at the task. So I mentioned this is a grammatical error correction task, and the input that I ran the models on is shown here. Both models correct this in the same way. I mean, both models produce the same grammatical error corrections, but they produce them in different ways. The Seq2Seq model has to emit 27 tokens from its autoregressive decoder in order to produce the correction where it capitalizes the first letter, it inserts I was before struck, and it inserts a before bicycle. As we'll see later, the edit5 model doesn't need to do nearly the same amount of work. But first, let's take a look at the computations that the GPU is doing in order to emit this output. This is a screenshot from the TensorFlow profiler. As you can see, it is extremely dense, but we will be focusing on only the things that are happening over here at the top. So how should you read this? Well, over here you have a timeline, and over here we have boxes representing the individual computations happening on the GPU at each time. So if you look at this area, I have it zoomed in over here, and you can see that the pink box over here corresponds to a matrix multiplication. One thing you can tell from this immediately is that the end-to-end latency for producing the grammatical error correction from the Seq2Seq model is 204 milliseconds. Now, depending on your application, this may be fine, but there are many contexts in which 204 milliseconds is too much. So you can tell, even here, that there are essentially two parts to this computation. First, this part over here, and then there's this remaining part here. So these parts correspond to the encoder and the decoder. So let's look at the encoder first. How can you actually tell that this is the encoder? Well, if you zoom in, you can see that it is composed of these 12 repeating blocks of the same kind of computation. And this, of course, corresponds to the 12 encoder layers in our transformer encoder. Now, the encoder here takes 15 milliseconds. And you can see that this is a very small fraction of the 204 millisecond runtime of the entire model. The decoder takes up the remaining 189 milliseconds. So if we look at a decoder step in more detail, you can see that for this model, this is a 12-layer decoder model, each decoder step takes 7 milliseconds. So if we do the math, you can see that 7 milliseconds per step times 27 steps gives us 189 milliseconds. So exactly what we expect the decoder, exactly what we know the decoder takes. So what can we conclude from this? Well, if we want to reduce the latency of our Seq2Seq model, we should target the decoder. And specifically, we should try to reduce the number of steps that the decoder has to make. And we should also try to reduce the latency of each decoder step. Luckily, text editing models are great at this. So let's take a look at Edit5 and how it handles this problem. So first, a quick refresher on how Edit5 works. Edit5 is basically a transformer encoder decoder, but with some additional components that, of course, make all the difference. So Edit5 has an encoder, as a transformer encoder decoder model has, but the encoder is also responsible for making tagging decisions. Specifically, it can decide to keep or delete tokens. Then there is a pointer mechanism, which reorders any tokens that are kept into the order in which they will be in the output. And then there is the decoder, which emits text that needs to be inserted at various positions in the reordered token sequence. So let's work an example. Let's say we have the input a long user query, and we want to, and the model has to emit the user query is very long. How it might do this is it might take a long user query, it might delete the first word, keep the remaining words, then reorder long user query into user query long, and then finally the decoder might might insert the at position 0 in this reordered sequence and is vary at position 2 in this sequence. So how does Edit5 reduce latency? Well, first of all, it uses a one-layer decoder. Now, I do have to stress, this isn't a technique that's limited only to text editing models. You could have a Seq2Seq model with a one-layer decoder. In our experiments, we found that a one-layer decoder is fine for all the tasks that we've tried Edit5 on. So grammatical error correction, sentence fusion, decontextualization. Now, the second thing that Edit5 does is that it moves work into the encoder. So specifically the keep and delete decisions and reordering decisions that we saw the model was making in the encoder side and not in the decoder. And the consequence of this is that Edit5 needs fewer autoregressive decoder steps. So how many exactly? So Edit5 for this GEC input only needs 10 decoder steps. Let's take a look at the latency of Edit5 versus the Seq2Seq model. So at the top, you have the same timeline that we saw before. At the bottom, we have the timeline for Edit5 to emit the same output, and these are to scale. So as you can see, there is a big difference. More specifically, the Edit5 model takes 33 milliseconds, and the Seq2Seq model takes 204 milliseconds. So there's a 6 times, so the Edit5 model is 6 times faster. Taking a look in more detail at the Edit5 model's latency, we see that it is also composed of essentially 2 blocks. The first is the encoder. The encoder takes about 20 milliseconds, and we see that this is about 5 more milliseconds than the encoder for the Seq2Seq model. And this makes sense because the Edit5 model has to, well, it has additional computation in the encoder that the Seq2Seq model doesn't have to do. Specifically, it has a few transformer layers, a few transformer encoder layers, and also it has a pointing mechanism resolution over here. So these total to about 5 milliseconds of extra encoder time. The advantage, of course, is that the decoder only takes 13 milliseconds. Now, if we zoom in on this, we see that a single decoder step takes only 1.3 milliseconds, compared to the 7 milliseconds that it takes for the Seq2Seq model. So if we take all of this information together, how does Edit 5 reduce latency? Well, the decoder step, the latency difference in decoder step in each decoder step corresponds to a 5.4 times reduction in latency per step. And the fact that the Edit 5 model only needs to run the decoder for 10 steps compared to 27 steps gives another 2.7 times reduction in latency, which in total results in a 14.5 times reduction in decoder latency compared to a Seq2Seq model. And this is all in exchange for 5 milliseconds of additional encoder overhead. But we should note that if you compare to a Seq2Seq model with a single layer decoder, this is only a 2.7 times reduction in decoder latency. Okay, that's enough about Edit 5. What I wanted to discuss here is an overview of strategies that text editing models have taken to reduce their latency. So the most basic strategy is parallel decoding. In a Seq2Seq model, each token has to be emitted, well, the tokens have to be emitted sequentially. Each token depends on every token before it. For text editing problems, however, we often find that it is possible to predict predict edits in parallel. So for example, if I have a grammatical error correction problem, I can capitalize a letter at the start in parallel with inserting a phrase in the middle, if these two changes are independent from one another. So if that's the case, you might be able to, for example, predict all of these edits in one go with just an encoder and have no transformer decoder at all. And as we've seen, the transformer decoder takes a lot of time, so this would be quite advantageous. Unfortunately, many models find that it is insufficient to just run a transformer encoder or to just run their model once. And they end up running their model a couple of times in order to account for changes that need to happen in order to be able to produce edits that depend on previous edits. So models like Gector, Pi, and the Levenshtein transformer they run their model once, and then they run their model again on the output of their previous run. And they do this a couple of times. Now, you might think that this will result in a huge latency increase, and it is a latency increase compared to just running the model once. But as we see in the table on the right, this is a table from the Gector paper, where we see that running the model once gives you 61.5 points of FO5, but running the model 2 times gives you 63.6 FO5 points. Running the model 3 times gives you 64 points. So you see that the returns are diminishing very quickly here. So you only need to run the model effectively 3 times to get all of the benefit. And running the encoder only 3 times is probably still worth it latency-wise compared to running a transformer decoder. Another strategy is to reintroduce autoregressiveness into the model, but try to limit the number of steps as much as possible. So both Seq2Edits and Edit5 and other papers like Chen et al. From EMNLP 2020, all of these models have an autoregressive decoder that only decodes the tokens that need to be inserted, and any tokens that are copied effectively are handled by other means. The Seq2Edits model also combines this strategy with iterative parallel decoding, meaning that they run their model a couple of times in sequence. Finally, what you can do is you can also use a pointing network for reordering, as the Felix and Edit5 papers do. And the point of this is to, again, reduce the number of decoder steps that your model has to perform. Right. So that was latency. And the other aspect that I want to talk about is data efficiency. So this is the other advantage of text editing models that we mentioned at the start. So on the left, we have results from different models on the sentence fusion dataset. Now, the x-axis here is the number of training examples that were available to the model. And the y-axis is exact match that the models achieved on the sentence fusion test set. So as you can see, well, the models, first let me introduce the models. The models that are dashed, like this one and this one here, these are Seq2Seq models. The models that are not dashed, like this one, this one, this one, they are all text editing models of different kinds. One thing that you can see here is that on the left side, when you have very little data, only 450 examples, the Seq2Seq models tend to perform much worse than the text editing models. As you increase the amount of data you have available, the Seq2Seq models catch up. And eventually they are just basically on par with the text editing models. Looking at the right, we see a very similar story for a different task, sentence splitting, where the Seq2Seq model here is trained, when it's trained on very few examples, so 100 or 1000 examples, it has a much worse SARI score than text editing models trained on the same amount of data. So what can we conclude from this? Well, if you have a lot of data, text editing models or their data efficiency is not going to be a huge benefit to you. But if you have only 450 or 4,500 examples, and this is not an unreasonably small amount of examples, given how having a high quality training data set might involve a lot of vetting by humans, and just in general, the cost of creating a high quality data set is very high. Given this, you might find that the data efficiency of a text editing model is very advantageous if you only have a limited amount of resources for collecting your training data. Finally, I want to discuss distillation. Distillation is a very well-known and popular technique for making better use of your training data. How it works is that you effectively train two models. One is a very large teacher model, and the other is a much smaller student model. The idea is that the student model is so small that you can run it in production, and the teacher model is too big to run in production, but you can run it for experimentation purposes. So the idea is that you train the large model on your data set. Then you use that large model to predict or to generate predictions for either the same data set or for a different data set. And then you use the outputs of the large model as the ground truth to train the small model. So this is a very well-known technique, and there are many variants of it. And it's very interesting to know whether text editing models also benefit from this. And it turns out that they do. So both in the Levenstein transformer paper and in Tarnowski et al. From ACL 2022, which worked on the Gector models, in both of these publications, we see that text editing models improve when they are given the outputs of a teacher model instead of original data sets. So in the case of the Levenstein transformer, these outputs were from a Seq2Seq model. In the case of the Gector model, the outputs were from an ensemble of other text editing models, with also Gector models. So yes, indeed, distillation works for text editing models, and you can use distillation to get even better data efficiency. Yeah, that is it for my talk, and I will now hand off to Eric for his final thoughts. Thank you.
Thanks, Jakub. So next we're talking about when should you be using text editing methods and when should you not be using those. And finally, I'll outline some possible future directions that will be interesting to explore. So say you have a text generation problem, or more specifically, you have a text rewriting problem or sequence transduction problem. The first question you should be asking yourself is, how much do the sources and targets overlap? So if they don't significantly overlap, say you're doing something like machine translation, then it's probably not a good idea to use text editing, because the basic idea behind text editing models is the fact that they can reuse significant portions of the source by doing this copying. But let's say you have this overlap, then the next question to look into is how much training data you have. And what we've seen in previous works is that when comparing a comparably sized transformer-based model, usually text editing models tend to give you better results when you have less than, say, 10,000 training examples. So that's one place where you should at least try text editing models. But even if you have a lot of training data, and I would say what the main use case, at least for us, has been, is to use it when you have very tight latency constraints, when you need to serve the predictions of your model in real time and you have tight latency budgets. This is really where text editing models excel. So if you either have only a little training data or very latency critical application, then you should be trying these models. And if you want to try these, here we've listed some of the open source implementations for various methods that we've discussed during this tutorial. So feel free and go ahead and try out one of those. If you want to get a compact summary of the topics we've discussed here and see the full list of references for the papers we've discussed, please go and check out the paper or the tutorial proposal, which you can find behind this link. So finally, what are some of the exciting future directions? Well, one problem I think would be very interesting to look into is, can we learn not only a model that decides between the edit operations, but also the edit operations themselves? Because I think the reason why text editing models tend to be sample efficient is that basically casting a problem into text editing makes it a simpler task because you have much smaller output space. And I think you could even further potentially simplify the task if you can kind of learn edit operations specific to your task, like some of the works, for example, in grammatical error correction have shown that carefully manually curated edit operations can make the models much better, but can you learn them rather than manually crafting those? Okay, second interesting future direction is looking into tokenization. So Alex mentioned already how important tokenization is and how important it is specifically for text editing models. So would be nice to do some kind of comparison of different tokenization approaches and maybe develop some custom tokenization approaches for text editing. Third, we all know the effectiveness of pre-training for various NLP tasks. And moreover, we've also seen how it improves text editing approaches. But can we design some custom pre-training objectives that would be particularly suitable for text editing approaches? Fourth, one topic we haven't discussed really so much, but with standard sequence models, one can sample multiple outputs using something like beam search, but at least many of these approaches don't directly work with text editing. So how can you generate multiple outputs if you want that from a text editing model? And finally, we've also seen the effectiveness of scaling up model sizes, whereas many of the existing text editing models, given that they mainly target latency critical applications, keep the model size pretty small. But what if latency wasn't that critical? What would happen if you started scaling up the model size for a text editing model? So I hope I've gotten at least some of you who weren't already familiar with the field excited about the different opportunities here. And I'm looking forward to seeing hopefully some of you making some future contributions, because as we've covered many times, I think it's a very practically relevant area with a lot of practical applications for cases when you have, for example, very latency critical use case. Okay, so with this, I would like to thank you on behalf of the whole team. And if you have any questions, please reach out to any of us.